Speaking of reliability, a podcast with good friends talking with you about reliability engineering topics. Welcome to Speaking of Reliability. This is Fred Schenkelberg.
And this is Kirk Gray.
Hey, Kirk. That sounded like radio voice there.
Well, I have to, because my name runs together with two hard, they make sure that they don't think it's Kirk Ray, R-A-Y, or something like that. Because Kirk and the hard K at the end and then the hard G sometimes
and it blends up together. Yeah. I don't get that problem. Everybody wants to know how to spell it for some unknown reason.
There's another Kirk Gray in Denver area. He's actually he's an engineering executive for Macmillan, I think.
Cool.
The book company.
Okay.
And I'm real surprised. I think, well, that's interesting. The same name and an engineer and
it could happen.
And education. He's in education. But
it's a small world.
I wonder if he listens to this. So go ahead.
One of the questions we got here recently, and this is, and it was, she sent over one of the parts of it I wanted to talk to you about was what makes a good, and she has quotes around good reliability engineer. And it was kind of his hard and soft skill set. And I thought, oh, that's an interesting question. I plan on asking almost all the hosts that will take it up with me, because I'm quite sure we all have a different way to answer that question. What makes a good reliability engineer? And before we were hit and record here, we were chatting about, do you add value? Do you add, does it make a difference? Does it change decisions or improve decisions or something? How do you know if you've reduced failure rate until you wait 10 years to see if it's actually reduced or not? Maybe you just pushed it off to 8 years. Now everything fails.
And you probably won't remember what you did 8 years earlier.
Oh, I keep notes.
And you don't come back and say, see, look what I saved.
No. That's number one rule is never say I told you so, especially when they ignore you and it is a big disaster in the field.
Right.
Yeah. It's not so one of the things is a little bit of humility. But what would your first response be? What is a good reliability engineer?
A good reliability engineer is one who asks primarily and first, why did it fail?
Mm-hmm. I would add a corollary. So the second question, I think, would be the first one is what might fail? What are the risks? Where are the areas that are likely to fail?
Right. Okay. Where are the areas that are likely to fail? And also
in prototyping and field data and everything else.
What have we built before that's similar? Mm-hmm. And what made it good or what made it bad?
Yep. But I think I knew your answer would be, why did it fail? It's do the root cause analysis, understand the physics, chemistry,
material science,
what was the decision and the information available that led us to the wrong conclusion. And then we had failures. And at that point, if you understand something, why it fails, the likelihood of you being able to influence the team to stop using that component or don't do it that way, don't put a blowtorch next to your wire leads that come into your components. It helps to understand what to actually do, as opposed to, and I think the opposite of it is, stuff was failing in the field, but we don't collect those or do any failure analysis. So just make it better. And you can have a team looking at you going, how? What's not working?
Right. It's just infant mortality.
We don't count that.
No. I'm sorry. Your infants sometimes get to be toddlers and even longer, and it's going to be a problem in the field. So, whether you call an early life defect, infant mortality unacceptable, which is a misnomer. Yep. It's a failure. It's something that.
Well, if it's 5% of your entire production, it's a 5% problem.
It's a 5% problem, and if it's just a matter of nickel replacement for the customer, whatever, I don't know, but it's basically asking lots of questions. The whys. 5 whys, 10 whys, and then understanding why those things happened or why, just keeping digging. And then also knowing some history and material sciences.
Yep.
Is this too hot? Is this going to be uh,
Is it,
causing distortion of the materials?
yeah, is it phase
And
change? Does it
yeah,
creep or move
right,
more when you're not supposed to? And if
right,
your dimensions are critical and you got this polymer race holding your bearings in there and it changes shape when it heats up, it doesn't take a material scientist to know that that might well be a problem.
right,
Um,
right. And is it going to be, where is it going to be used? Is it going to be a printer on a boat in the ocean?
yeah,
Is it going
you
to
love
be
that story.
right? Because, I think engineers are very generally, the design engineer are somewhat conservative on the potential use and locations and stresses.
Mm-hmm.
And, they would say, well, the customer's not supposed to do that. Well, the customer shouldn't be putting it there, or the customer shouldn't be using it in that environment. Well,
Well, part of
sorry.
it too is I think what makes a good engineer is that while I could imagine that it's being used on a charter fishing boat in the ocean with salt fog and hosed down with salt water and all the other
Yeah,
stuff,
right,
we could design a product that does that. But of the million printers we
right.
sell, only 3 of them are going to be in that situation. So how about we not design it at $8,000 a copy? Let's make it
Right,
at $200 a copy for the other 900,900, so on,
right,
folks. And then there's a
right.
handful that are going to store and use it in a snowbank because they like you sitting in their ice fishing shack with a
Yeah,
printer available.
exactly.
Like,
Exact could be.
yeah,
Yeah.
let's not count those people. And but there's
But
some,
they're gonna put the printer in their mobile, their RV or whatever, and it's
yeah,
gonna bounce around
bounce around a
the
bunch.
back of the trailer or something. You just can't.
Well, you
You
can. That's the issue. Is what
you
makes a good
can, but
reliability
it takes a lot
engineer.
of effort
Yeah,
to.
but I think that's where a reliability engineer says these are all ways it could fail. These are all viable scenarios. We have field
Mhm.
history of them, all this other stuff. But I think what makes a good engineer when it comes to failures and understanding which failures that we need to solve is understanding that context. This is, yes, we could. We're not going to make specific products just for maritime use or RV use.
Right,
We're going to make ones for people that print at home. They put it on a shelf or on their desk and they print from
right,
that, and that's it.
right,
And we're not going to cover it from every possible scenario because our market won't buy it. The 900,000 plus won't buy it if it's
right.
$8,000. So it includes the the cost benefit, the trade-offs that we have to make and understanding that. And that's where I think we make a great difference, is understanding that we're not designing for the margins, for the exceptional cases. We're designing for the 90th percentile middle group that uses it in an office or at a home.
Right.
Yeah.
But we know that also that if we make it as robust as it can be with standard materials and manufacturing methodologies, that it's going to be much more reliable in a wider variety of situations and
Yeah.
conditions and stresses. And, not that we know exactly what these margins are for every situation, like salt spray or things like that.
Mm-hmm.
We know that in those kinds of situations, we might either customer knows that, it's aware, say, for instance, if it is going to be on a boat that's going to get a lot of salt sprayed to the window, they put it in a box, or they put it in a container that's a
Mm-hmm.
sealed,
Well, they give
protected
it
for it.
some protection for it,
Right, right.
but I think some of the thing is, well, oh, they'll honor the warranty. you know,
Yeah.
there's
Well,
there's
yeah, because
other
you're not gonna.
factors in the
No,
decision.
yeah, there's no question that when you send that back, you're not going to tell them how you used it or where it was.
I know, but part of it is the reliability engineer is one. I totally agree with Kirk. Is let's design a robust product, not
Right,
one that meets the letter of the spec. If it
right.
works at 40C but it doesn't work at 41C, that's not good, right? Let's have some margin on all these different stresses. So part of it is understanding the stresses and helping the design engineers understand
Right,
this is the likely way it's used or how it's used or how often it's used, those
right.
kinds of things. So they have they're informed to design it appropriately for the bulk of the use cases.
Right.
Now, don't ignore the weird cases, because let's say charter boats, fishing people find that printing a photo of their catch is really good business. And now all
Right.
200,000 boats put
Right.
printers on their thing.
Yeah.
Now that gets expensive for warranty, because they're shipping them back to us every 3 months.
Right. If they're failing because of that.
Right. But if it's a couple 100,000 people doing it, well, we might want to
Make a marine version,
make
or
a marine version,
or add
conformal coat them, or whatever
coating on the boards.
And it's a cost benefit trade-off. If there's enough of a problem in our field data, or in our perceived where it's going to be used, or let's say the fishing boat charter consortium.
Yeah, it makes a marine version of a printer. I don't know.
And helps us, get that market and does or whatever. It may make financial sense to do that. But it's part of the picture, I think, is understanding that material science, the chemistry, physics, the nuts and bolts of truly understand how things fail and why they fail.
Right.
And where's this fit in the business? How does this make business sense? If we fix this, it saves us one failure the next 400 years. Well, I'm not too sure I want to go spend money to do that.
Right.
Whereas if this one fix saves 80% of our products and they now can last for 10 years instead of 2 years, somebody will nix that, saying, well, then we can't sell a new printer for 10 years.
Right. It's just how precisely that 80%, what you're saying, projecting as far as what we're going to save. And this is always where you err on the side of maybe fixing something that you're not absolutely certain. You've seen it before in the field, but also, it's becoming, the product's becoming more widely used in different locations. I'm sure there's, examples of that, of where something wasn't very robust, and now it's pretty tough, and you can put it in different situations. But it's always a difficult estimate, and you don't have any way of proving that you've saved. Like, again, we talk about the smoke detectors and how much they've saved lives, but we don't really know how many lives it saved.
I bet you one of our listeners is going to go, I saw
insurance,
a study on this.
Well, you're
insurance
right.
companies probably do.
Insurance companies do, and they know, but it depends on where you put where you put the smoke detector, how many you have distributed through your house, how close you are to potential sources of fires, those kind of things. There's a lot of variables in that too.
But at the insurance level, they got to write they pretty much demand
the policy, right?
Yeah, they demand you have it. And our local county ordinances, they come out, and I had some windows replaced, and I had a permit for it. And the only thing they looked at was, where's your smoke detectors? I'm like, okay, we didn't expect that, but we got them. They work. And
right. And it's an amazing and wonderful invention that saved lots of lives. And, it's good. We'll still have fire departments for sure. Then smoke detectors don't prevent fires. They just tell you that there is one.
Well, that brings up a good point. It's one of the aspects, and I suspect you would agree with this, is that a really good reliability engineer prevents problems. You and I can look at a design going, have you thought about, or what about this? Or we just did a halt and we're not shipping yet. You still have time to change this design. You might want to make, this change, or here's the evidence, here's the problem, here's the physics to it.
Right.
It's not so much doing failure analysis and then after the fact. I think that adds value, but it's not near as powerful as preventing the problem right in the design, right from the start. It's a bit of experience. It's a bit of using the information you have. It's understanding failure mechanisms, so that you can look at a product and go, is this where you're having problems, or is this is likely where it's going to fail? And then, you run a test and it proves out exactly right.
Yeah.
Those kinds of things, I think, are a hallmark. And it's not so much, hey, this is never going to work. It's more the soft skills come into play, going, here's the evidence, here's the information, here's the risk, here's what the possible solutions are that won't cost you a whole lot because you're so early in the design.
Yeah.
we're not the one making the decision, but we can sure shape it and influence it. And I
Right.
think those
But it
save
does
tons
take
of money.
yes, it does take soft skills too. And you do have to build up relationships. You do have to build up some uh credits
Hmm.
before you start, asking for changes and showing and trying to, get people to agree with you. You have to be somewhat agreeable.
You got to be, yeah,
Yeah, you
a
can't
part
just
of the
say
team,
you can't
and
tell people you're idiots and you don't recognize.
yeah, that doesn't work very well.
That doesn't work very well, but I guess a lot of engineers and have on the autism or
I would go. I
on the
would go.
spectrum
I wouldn't go that
sometimes.
far. They're
Sometimes.
well trained. They got experience. They know what they're doing, and they also, besides just reliability, there's like 15 other interests. Saying, "Oh, we need to make it environmental. We need a cost reduction. We need to
Right.
do this. We need to do that."
And we're not even talking about also the manufacturing
Oh
variations.
yeah, and they're going
What
to be
can
all over
happen
you
during
too.
that? All
Yeah.
over. Yeah, we've got to
Yeah,
find
and they're
capable
all over that. But
yeah.
but the
Right.
idea is that if you're going to bring a problem, you got to bring the ability to help find a solution, or look for a solution, or compare things, or
Right.
add
Right.
resources to help
That's
solve the
right.
problem. And it's part of the building the credits, or the trust, or the
Right.
reputation that you know what you're talking about. And then on the financial side is understand what's the impact. Let's not go all crazy and try to get something fixed that will cost more to fix than it'll ever save.
Right.
Your
Right.
credibility
And
be gone at that point.
no, yeah, you die on that hill that's uh
A 40
five
cent problem.
right, 40%, 40-cent problem and or stop a program because you're saying it's 5 degrees over this, capacitor's temperature, recommended temperature, whatever. And I'm
Yeah.
going, you guys, component
Yeah.
specifications
Don't mean a
uh,
whole lot. Yeah.
don't mean a whole lot because,
But you're bringing a bunch of experience to it because you
oh,
understand and have
exactly.
evaluated all this stuff.
Exactly.
So
That's
I
a
think
part
it
of it.
takes constantly
Real life
learning, real
experience.
life experience, constantly learning, constantly looking at going, why did it do that? Why is that happening?
And even though people want to stay with the same company, I recommend they move around and eventually become consultants so they can see the big picture with and commonalities between a lot of these manufacturing and design
But not today, guys.
organizations.
Not today. We don't need the competition right now. Just being facetious.
Well, yeah, okay. The younger generation is coming along, and I was happy to hear Chris talk about a younger crowd, maybe at Rams,
Hmm.
but I'm afraid they're learning the same silly Arrhenius-based MTBF stuff, and that's what I really is really distressing. And like the paper I have on my website, and I put in all the notes of these podcasts, and that is reliability prediction, a continued reliance on a misleading approach.
Okay.
And
Well,
that was by the US Army. They wrote it.
I know. But the idea, though, Kirk, is that to be a good reliability engineer is check your assumptions.
Right.
Do the due
Do the
diligence,
math
understand it, do the math, do the studies, read
and
the
get
technical
your hands
papers.
on the product, touch the product,
Yeah, don't drop
open
it
the
unless
product.
it's don't drop it if you don't want it to fail. But
Yeah.
yeah, you got to
Yeah.
understand the product really, really well, and
Yeah.
all the technologies in it. And it's funny, is years and years and years and years, and I think still today is capacitors lead to so many failures in electronics. And it's not that they wear out or anything like that.
No.
It's they're mishandled, they're ignored because they're just everywhere. They're like
Or they're mismanufactured.
either they're mismanufactured, or they're damaged in manufacturing, and then there are design problems that occur too.
Right.
And but the idea was, is that, I'm talking to different failure labs at one point, trying to go, what is the Pareto of do people bring you to help solve? And they were like, 30 to 40% of the problems are capacitors
Yeah.
of what they see. People bringing in products and stuff, and it's a capacitor. And I'm like, wow, it was number one by far on a Pareto chart of types of by sorting it by components being the issue.
Right. Well, you can also break it down to types of capacitors because
Oh
you have
yeah, yeah.
MLCCs, ceramics, aluminum electrolytics, tantalum.
Yeah, and they take turns being the problem child at
Yeah.
different points in time. But the idea is that just because the whole team is focused on this new widget CPU whiz kid component and it's the new braking technology or whatever, and you're using sockets and all the other weird attachment methods. And
right.
one of my favorites way back when was fuzz buttons. You remember those?
Buzz buttons?
Yeah, it was like a little piece of Brillo, wire mesh type stuff, kind of all crumbled together, and it was kind of spongy. So it would take up differences in height and still be electrically conductive. And like,
where was that used?
Under chips, under BGAs in sockets.
Huh. Okay.
Yeah, and it was okay. That's a clever way to take care of the variation. What happens if this spring becomes set and it doesn't spring back anymore? And you replace the chip and it doesn't make contact. Oh, that'll never happen.
Yeah.
How do you know that?
Famous last words.
Famous last words is that.
That'll never happen.
But it's understanding the technologies, understanding some material science, understanding those things, and asking what if questions. FMEA is a great tool because it helps you ask those questions. How could this fail? When will it fail? And then that feeds into HALT. It's like, well, let's see what actually fails.
Right.
And you and I
see the variation in those two, where those failure points are. And that's one thing I've tried to emphasize with HALT, that somebody said, well, we didn't see anything. No, you did. You either saw consistent boundaries, same limits were very close with all your samples, or they weren't. And you had a wide distribution in whatever this mechanism was, or you had a bunch of different mechanisms. You learned a lot.
I had one of those in a drop test. It was a handheld, like a microphone for a game controller.
Right.
And we did drop testing, and one of them failed at 20 drops, another one failed at 40 drops, another one failed at 120 drops.
Right. And that was incredible information.
Yeah. So we took a close look at it, and it was like, oh, the one that went 120 drops had a glue line that went all the way around. It was 100%. The one at 20 drops only had about 30%.
Right.
And so we did a quick test, and this durability of this thing really was correlated to how much adhesive was actually used.
Right.
So we walked upstream to where this thing was attached, and they says, well, the volume was getting too high, so we had to use a manual process.
Right.
Now, the automated process, which was qualified as being part of the manufacturing process, was automated, and it did 100% glue line.
Right.
And it was, and it had an optical thing to check that it actually did. So if it had a bubble and missed a spot, it would go back and catch it. It was a really slick machine.
Yeah.
But the guy next to him, the machine had a syringe and would stick it on. And it's like they're being pressured to keep up with this automated system. And they're like, whoop, 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 whoop. Like, okay, what happens? The one guy you train goes on vacation or is off for a shift. What do you do then? Oh, Sarah can handle it. She's seen him do it once.
Yeah.
And I'm like, okay.
This is a very good example of how machine-built things are much more reliable than hand-built things.
If built really well.
We have built well, but automatic. I think anybody doing a resoldering is going to be not as good as a reflow machine doing the initial
I have
soldering.
evidence to that. We did a bunch of studies on that.
Yeah.
It really cut down the life of the solder joints.
Yeah,
seriously cut it down.
Yeah, exactly. So those are so many factors. You've just brought up all those factors that weigh into our subject.
A good reliability.
A good reliability engineer. He's got to have a little bit of experience with all those kind of groups of people, whether it be a manufacturing quality or design guys and
finance. Don't forget finance.
Finance, yeah. There's, it requires being able to cross a lot of the silos in a company, and those really can be very difficult to break through sometimes.
And if you do your homework, you understand the failures and failure mechanisms, and understand the business processes and what's important, and not important, you can go quite a ways of making a difference.
Right.
And then And don't be shy that,
Right.
you just help make a decision that saved, $1 million. Write it
Right.
down so that later when somebody asks you what you
Right.
did, it saved $1 million. Here's the
So, yeah.
evidence.
Right. And so a really good reliability engineer is 60 or older and had real experience and had 30 years experience
in
with
15 different companies.
15 different companies with biomedical, computers,
Aerospace, don't forget aerospace.
And
downhill well drilling,
yeah, that's difficult to do. Most people want to stay in the same company, and stay employed consistently and not take risk.
Yeah.
And not take risk of pushing the boundaries in the company of making a bunch of noise and saying, we really should be changing this. And then later saying, I told you so.
Yeah, it doesn't help. It doesn't help at all.
You won't win any friends.
No, we could write that book, is how to alienate people and piss everybody else off.
Yeah, it's sometimes, it's like you may win the battle, but you lose the war.
Yep.
And that can be, disheartening, but you learned a lot in every case. If you fail in a job, you've learned a lot.
Well, if your product fails, you have a chance to learn a lot. It's the way we think of it. So
I guess
you don't
want it to happen, but
yeah. But anyway, there's obviously more to it, but I think we outlined a good piece of it there, Kirk. So thanks for taking that on with me. I'm curious how the other hosts are going to take on this question.
What makes a good reliability engineer?
What makes a good reliability engineer? And I'm very happy it's not spelling. Although I'm going to try to spell out a URL here in a second.
I know.
So,
but we've gotten better tools, especially for us, for engineering. Engineers aren't the best writers. And now we've got some great tools like Grammarly and others that help us really make it sound much better readability. And things.
Yeah, no, that definitely helps. Now, if people would actually read, that'd be great. So it's a whole other subject. Yeah. But if you're listening to this, not reading it, because we don't offer transcripts, but you're listening to this and you go, yeah, I would add fill in the blank. Let us know. Send it on over. Because I plan on holding these kinds of discussions with a handful of the other hosts and see what kind of takes they are. So I'd really like to hear from you. Is what do you think should be a hallmark of a good reliability engineer?
Right.
Let us know. Head over to accendoreliability.com/go/SOR. I think I spelled those words correctly, go and SOR, or said them correctly. There's a couple ways to get in touch with us there. Kirk and I and the other hosts are available through LinkedIn and our About pages. So plenty of ways for you to get in touch with us. Another hallmark, Kirk, another hallmark of a good reliability engineer. Yes. You're available to answer questions.
That's right. Let me just say, also, if you're using at least my Apple podcast, there is a transcript. It's automatically generated.
Oh,
you can read our whole discussion. It's completely done.
I'm afraid to look at that. I'm afraid to look at it.
It's interesting. They do a pretty good job, unlike Siri on some, translations, whatever.
Yeah.
And the dictation.
It
does a very good job. And you can go to the show and you'll see they've completely
should be able to search it too,
transcape.
Right?
Yes, I think so. Yeah. I think so.
That's cool. I didn't know that.
You got to check it out. So anyway, if you do want to read it, go ahead. But I'm sure you love hearing Fred and our voices. So, and I don't think you catch our laughter and humor with the
transcript.
Yeah.
Yeah. So anyway, let us know. We'd love to hear from you one way or the other on this topic or anything else that's on your mind. So let us know. All right. Thanks so much, Kirk. Have a great rest of your day.
Okay. You too, Fred. We'll talk again.
All right. Cheers.
Okay. Bye-bye.
Thanks for listening to Speaking of Reliability. We invite you to join the conversation. If you have a question or a topic that you think we should discuss in a future show, please let us know. You can find a comment box below the episode show notes, or just leave a note as part of a review on iTunes.